So, all right, we can start this now. I'm that guy, also that iximeow on the Twitter and like every iximeow that is on the internet, other than that. Hello? It sounds like, okay. Now I have a microphone. All right. I'm going to be talking about JavaScript Deobfuscation, particularly automating it and trying to automate it in a way that you are certain that the program you get out is correct. There are some tools that will try to deobfuscate and try to say, oh, I have this string, I'll replace this with the other string, and introduce subtle errors. And I want tools I can trust, just as a general rule. So here's an approach that would be correct, not necessarily as good, not always as good at removing some things, but always correct when it doesn't change. That's done fun stuff. JavaScript is everywhere. Obviously, web browsers, HTML, things like that. It's Windows script host can run JavaScript as well. That's what really motivated this. I work at a company where some people who deal with endpoints that have been compromised. Sometimes the first stage of that is you got an email with some zipped JavaScript attachment that's totally your legitimate UPS delivery notice, and it's not. It's some JavaScript that you ran, and it did a thing, and it downloaded something and ran it. And a fairly reasonable question is, well, what did it do? What did it talk to? Because maybe we have this email and we don't have everything else. Node.js, of course, is a way to run your JavaScript. Obfuscation, as I'm talking about here, doesn't apply to that as much because minification is a little bit different. Obfuscation I'm talking about here is intentionally rewriting your program to make it really hard to understand as opposed to just making it as tiny as possible. And then as like just shout out, MP Engine is awesome. Where Windows Defender has a JavaScript runtime built into it that will emulate JavaScript that hits your disk to see if it's malicious, which it does in the kernel without sandboxing. There is the fun bug in Windows Defender a few weeks ago, I think. So yeah, Windows Script Host. If you double click on a .js file in Windows, this is what runs it. You may really pray that it's sandboxed and isolated, like you run some JavaScript, but it's not going to do anything too bad to your system. No, you can just literally make yourself a shell. And this is a thing that happened just by digging around on the internet for dates. Around 2012 or so is when this kind of started showing up. So, all right, obviously they're going to try evading malware because malware is going to look for this. So do something to try evading AV, evade spam detection. So, WScript create object, WScript shell, literally making yourself a shell looks kind of sketchy. So let's have an idea here. That thing is simple and straightforward. The other thing is the same program, but significantly harder to just eyeball. And if you're just looking for the string WScript.shell, that's gone. If you're looking for create object, the string in your source code, that's gone. So there's a few tricks to make just like blindly looking for source code not work so well. And this started showing up as far as my digging would tell me around 2015 or so. So relatively recent, but all right. So we can walk through this though and see, well, what is it doing to be obfuscatory? What is it trying to do? What is it hiding its behavior? How is it hiding its behavior? So string from character code is really common. You have string from character code, some constant, which turns into a single letter string of whatever that ASCII value is. In this case, R. So we have on the left, it ends up joining up create. This construct does an empty object plus string, which gives you this object string. That's just what JavaScript does. And then immediately after, we just index into it for the word, which we get object out. And that's how we get our word object without using the letters, object, any of those letters. So this entire structure on its own is an alternate way of phrasing wscript.createObjects. The array notation in JavaScript is how you can access members of objects too. If you get the member of an object as a function, well, you can put parentheses after that and call it. So this happens to be equivalent to the original code. This one here is kind of hilarious because we're replacing the original word with a new word that maybe contains it as a substring. Same idea holds, though. We look for the word run out of it, and that's how we get some command that we're running with our shell that we've made. So in the end, we go from our obfuscated string back to we can at least understand what the original code was. So the general idea is, what if we automated this kind of approach? By hand, it's kind of annoying. You can write a script one-off to deobfuscate your one thing, but if you change the layout of your file, if you change your approaches to changing the names that you're generating or how you're generating your substrings, those scripts can be brittle, even though they're correct for one or two samples. Computers are patient, so obviously you can write something that obfuscates itself and then obfuscates that and keep going for, call it 10 minutes, and then you run that. That's not a thing I've seen much, but mostly I suspect on the basis of it hasn't been needed, because no one really tries to deobfuscate this because they assume that's hard or the approaches are brittle and don't worry about it. Just try to find whatever happens some other way. This is an example of some actual JavaScript malware that I've seen. This is the delivery notification thing. So we have some text up at the top that's just like gibberish. The variable names have been totally mangled, and this goes on for 200 some odd lines. That's just a bunch of junk. So that's what you kind of see in real JavaScript obfuscated malware. But repeating this for every script is really just awful. So there are tools that will try to deobfuscate your JavaScript. What they'll do is they'll take your JavaScript in and they generally assume they're trying to unminify. So you have some JavaScript where you replace all your variable names with tiny one-letter things so the actual bytes you send over the wire are smaller, so the JavaScript payload for your website is tinier. Totally legit thing to do. Makes me feel a little bit sad that we need to do that, but that's how JavaScript in production websites ends up working. That doesn't help this at all, because maybe we can rederive some meaningful names here, but the problem is the overall formatting and just the other things that are happening in this code, such as this line where we're appending some strings together. Trying to unobfuscate the names alone doesn't help too much. So it's good for augmenting anything that we're doing here, but not on its own. The other problem with some of the deobfuscation tools is that they will run your JavaScript in the browser, which is a problem because you're taking actively malicious code and then running it in a variant of the intended environment, hoping that you stopped it from doing bad things. Sometimes they're standalone tools. They'll just take Node.js and like shove some stuff on top of it and try to catch bad things happening. That scares me. Like I was saying, a lot of it focuses on minified JavaScript rather than trying to fix up structure, clean up the code. Chrome's pretty print is also a good one for just some of the, just jam some stuff into a single line and try to make something useful out of it. But again, doesn't help you try to automate the actual process of simplifying out dead code. If you can prove that something is never going to be reached, well, why would you put it there? Just to confuse people. Don't notice that slide. So this is another funny thing. A lot of JavaScript deobfuscation tools will try to replace eval because they'll assume you're trying to run your code with eval, but you can just create a new function with that textual code as the body and then immediately run it. Constructing a new function this way, you can do things to stub this out in the runtime without getting too invasive, but you run the risk of breaking legitimate programs. If you try to intercept this and do things, you will break some good programs. So yeah, the stubbing eval and moving on with your life and running things isn't foolproof. And in the same way, other techniques that are other tools in various JavaScript environments might not get stubbed because you might not know what all's out there. if you try to detect your environment, if you say, well, if I'm going to look for XML HTTP request, and if that exists, I know I'm in a browser, but I was targeting desktop users. So if I'm in a browser, but I'm supposed to be on a desktop computer in Windows script host, you're clearly looking at a situation where some analyst has picked up your code and is trying to reverse engineer it. So, well, change your behavior. Do something that looks malicious, but not the same thing that you were initially trying to do. And now you've significantly compounded any kind of reverse engineering. One idea that I was thinking is, at that point, why not make a request out to your machine and say, oh, I know someone at this IP is looking at this, and maybe here's how they've changed the script, because you can get the text of the script that was run. So yeah, just outlining that exact same train of thought. I know people who are doing this for languages that are not JavaScript. I haven't seen this for JavaScript because I don't think people care enough yet, or ever, maybe, we'll see. So this doesn't work out so well. Let's change the size a little bit. All right, so trying to run known malicious malware. Let's go back. So let's stop running known malicious malware in environments that are at least amicable to what it's trying to do. What would we do then? And at this point, you drag in compiler theory and you think, oh, well, maybe I'm going to build something similar to a compiler, because we're taking a program and we're trying to give a different but simpler program out. It's a well-known thing that compilers do all the time. Super simple diagram of what a compiler does. You have some code, it goes into a parser. The parser produces some more abstract representation of that same program. You do things to that abstract program. In the case of C, you produce, the machine code. In our case, we're going to take some JavaScript in, do some stuff to that JavaScript abstract form, and then render it back out as code. Some of the problems can be solved simply by parsing the JavaScript and getting that abstract form. The rest of the problems can be solved by more in-depth considering what the JavaScript, what is defined for all of the behaviors. What happens when you add a string in an object versus adding an object in a string, because that A plus B equals B plus A is not necessarily true. Writing a parser is kind of tiresome. Getting the parse rules right for JavaScript would be really important if you wanted to write one. So I'm just going to use someone else's, and that is what I have done. It's good enough. There are some cases where it can cause problems, but that's more advanced than something I haven't seen in the real world either. So kind of obfuscations I've seen, in addition to just restructuring a program, is trying to embed all of your strings instead of like the plain ASCII is hex of the same thing. So this is capital A, capital B, capital C, capital D, capital E, just as hex. So if we parse this as a JavaScript string, though, we can just replace all of the hex with ASCII and be good to go, because we know where the string starts and ends, and we can just look for all the cases of \x, whatever. So literal code that you would do to do this, you get an instance of your parser, parse that string, and you can see that the value of that string is the literal ABCDE. Cool. In all the cases that we would have had weird hex in our strings, this solves that pretty well, and robustly too, because this is as correct as the JavaScript runtimes themselves are. Another case that happens is, you've crammed all your stuff into one line. You've used weird constructs like, what is the negation of an empty array? Is that true or false? So by just parsing and printing it out again, we can still see results that are pretty all right. Remember earlier, the actual real cases of this can be pretty nasty. So if we parse this and print it out again, we have a fairly large, this is tiny because the actual program I was looking at is quite tiny, but this is the abstract form I was talking about. So at the very end, we can see the enclosing object is a program where inside it has a sequence of, here's the test for the if, where we were doing negation on the empty array. And this is what a lot of code that I've written for this actually works with. So we print it out again, we take that abstract form, render it back out, and now it's a lot more reasonable to just eyeball. The code itself is still confusing because what is the negation of empty array? What is the double negation of empty array? JavaScript has many ways to hide your actual values. So if you remember the first line of that file before, we go through and we have this big old line of stuff. Well, we can parse that as JavaScript, and let's see what we get. Reasonable. Like, you can actually read this and make sense of it. You see, we start with some date. In this loop, we get a date for whatever now is, compute the difference, and if it's more than 7 seconds, we break. Not even needing to like fix up names or anything, just parsing this out and printing it out again is good enough to have something helpful. As far as the abstract syntax tree trickery, the abstract form of these programs goes, parsing and printing it back out is pretty easy, pretty straightforward, and I'm considering kind of low-hanging fruit. There are some caveats to that where just by parsing and printing out again, you can break the program. There are obfuscators on the internet, particularly one on GitHub, where it has a mode that takes your big old JavaScript in, obfuscates it, and if you change it at all, the program stops working, which is kind of interesting. Everything else, though, everything else I'm going to talk about involves actually traversing that abstract form and seeing, well, what does this do in the context of the program? Is this going to be, can I make a change here and will that be safe? So this is where we get into more of the in-depth kind of analysis where, so say initially we had our Wscript create object again. We can start replacing this with array indirection to build up our strings. So we replace the Wscript part with the first entry in an array. Do the same thing with our period, with our shell, and later on when it goes to run, as long as this array has not been changed, you just concatenate those together and you still can build your Wscript.shell string and still be sufficiently confusing to anyone just trying to reverse engineer JavaScript. But in order to do this, we need to verify that our randomly named array is not modified before it's used. If the initial array is modified, we can't just reach in there and say, oh, well, this is a constant value, and grab it, put it back in. We have to make sure that there's no variable scoping weirdness. We have to make sure that that variable actually refers to the array, because maybe you've done some kind of trickery with names where in this line, it becomes a string. So we're indexing into a string and doing something different than perhaps what an incorrect analysis would tell you. After you undo the obfuscation through the string array, though, it looks pretty straightforward. You would build out your Wscript dot shell. So this is an example of where things can be kind of confusing. Say you had a decode function that replaced all of the entries in your array with some decoded value. And, say it was Wscript, but you decoded into something else. Maybe literally Satan, like the command was before. You have to be really careful when you're traversing over the object to say, well, are we reassigning to this array? Are we reassigning to any elements in it? Another one that I've seen a fair amount is base 64ing some parts of your code where you have some string and you base 64 that so that in the source code, the original thing is gone. When you go to run it, you just throw a decoder function in front of it that would debase 64 it. In that particular case, we maybe can do something really nice where we just say, this string looks like base 64, and alongside it in the code that we write out, maybe insert a comment from us that says, oh, this is base 64 of that text. So this is base 64 of something that looks like JavaScript. Maybe pay closer attention to this particular variable. And same kind of situation, so if we had an array that was just used to break apart the wscript.shell string, just base64 each of the components of that array, and then later on decode it and then use it. One of the other things that you see is, well, compute some code and then eval it, run it again. In these cases, it's usually pretty common to see something like a first stage that downloads something, hits a web request, gets a result, does some stuff, evals what it got from the internet plus some decoding. Sometimes enough of that is included locally that you can do interesting deobfuscation and know, well, whatever comes in from the internet, I'm going to prepend this stub that's going to put it at that location and run it. If we can analyze JavaScript source code, though, and we can compute what is going to go in the eval, we can also try to deobfuscate what goes into the eval. So that's cool. Eval looks like a function call, just the same. So we can just look at the single, hopefully constant argument. Another thing that happens a lot with obfuscated JavaScript and minified JavaScript is you'll see like negations of objects plus objects, or bitwise inversions of array plus empty string. That is absolutely just relying on trickery in how JavaScript operators are defined. They're defined by the language to do one thing or another depending on the type of their arguments. So you can know that you replace the literal word true with negation, negation, empty array. You just end up sitting and messing with it until you find something sufficiently confusing. Thankfully, there's a finite number of permutations to this, though. There's roughly 8 types of JavaScript things. There's a 9th one that I consider as well for some of this code. So we have numbers, which are all the floating point numbers, all the integers. Nan, which is a special number that is not a number. Lists, arrays, things like that. Objects, which are more like maps and dictionaries. Strings, functions, undefined, and null. JavaScript having both undefined and null for various reasons. So that gives you 72 pairs for each of your binary operators that you'd have to look at the types for if you want to go through and be as pedantic as possible about it. I'm kind of lazy, so in the code that I've written, I don't want to have to go through all 800 cases, roughly 800. So going with just plus and minus is good enough for a lot of obfuscated JavaScript. And if I run across binary operation on 2 things that we don't know, then we just say, well, I don't want to look at this anymore. Just don't change it. So the other kinds of obfuscation that we've seen are when you take a string like that, and like we saw in that first sample, just break it apart into smaller strings, replace some of them with some kind of obfuscation. But the nice thing about this is all parts of this expression are constant. Percent's always going to be the string percent. String from character code 80 is always going to be capital P. So if we were looking at this, we could say, well, is everything all the way through this expression going to be constant? If it is going to be constant all the way through, just compute it. That gets into an interesting question of how dynamic do we want to be, how much code do we want to run. But if we restrict ourselves to only running any code that we can prove to be constant, that's pretty safe. We're not going to run arbitrary function calls. We're not going to run evals. We're only going to say, well, what does JavaScript say this expression reduces to? Like I was saying, if all the parts are constant, it doesn't matter how much stuff has been done if you can just define consistent rules for what exactly constant means. Maybe you say, I don't want to use any function calls when I'm trying to reduce these expressions down. So you say, well, I can add strings, and I can be well and good with just adding some strings together. But I don't want to compute string from character code. Well, even partially trying to simplify this can be significantly helpful. Some function calls, you can determine them to be constant with respect to their arguments too. So in this particular case, we have a function that does stuff. It takes an argument in and subtracts 0, which is a JavaScript way of taking a string that looks like a number and giving you actually the number, and then indexes into the array with that. So when we call a with 0, we actually subtract 0 from the string 0, which gives you the number 0, which is the index into the array to give you the string A. Right? There we go. Nothing changes, though, when we actually run this program. So it's safe to make this replacement, replace the function call of A with 0 with the value that function would have returned. And now maybe we can start simplifying out these programs. That can get pretty involved, though. You have to look at, does this function call any functions that call any functions that call any functions, all the way down to anything that might not be constant. If you touch things like runtime code, well, you might not know what the platform's APIs are. If you're just looking at Windows script host code, if you're expecting to look at things that are running on Windows, you're not going to look for XML HTTP request because you wouldn't define it. You don't want to try to assume that those are constant. So personally, trying to be pessimistic, I don't want to be wrong. We assume that anything that isn't defined probably isn't safe to replace. We have to look at scoping pretty carefully too, because there's that same kind of scope trickery where if in this function I have shadowed a variable that is in the enclosing scope, I need to be sure I'm referencing the right one when I'm computing this out. And of course, no functions here can assign to anything outside their scope, because if I assign to a global, it matters if I just rip that function out and replace it. Any assignment to a local variable, any assignment to anything that's not a local variable is bad, is a safe assumption. It's also fair to say any undefined function means just stop right there, don't do anything else, just quit out. A lot of this relies on, is this particular value that I'm looking at, like this particular value, is it a constant? It's a pretty well-known problem for compilers, because LLVM looks at this and has to do all of these kinds of analysis to say, well, is an optimization safe? And in reality, a lot of these problems turn into the same kind of problems that compilers do when they're doing optimizations. So LLVM, GCC, G++, the Microsoft compiler toolchain, JVMs, all of your runtimes do things kind of like this, and even JavaScript runtimes. I don't want to lift C out of them and try to deal with C, though, so the code that I'm using here is more DIY in Python with the parser that I mentioned before. So you want to tell that a function call is constant. Is it a function that doesn't reference anything that's undefined in isolation? Does it reference anything that could possibly be reassigned? Are all of the arguments of that function safe to evaluate? If any of those cases are false, it's not necessarily constant. You can't really know for sure. So if we look at this particular example where we look at, in isolation, this particular thing, well, it calls something undefined. We don't know what A is, just from this line alone. Nothing here can be reassigned, which is nice. And the arguments are not safe to evaluate either, because we don't know what B is. So we can't actually do anything here. Better example, though, is if we have a function A, it doesn't really matter, takes an argument, returns that argument plus 1. Call it with a constant. Well, all of the call targets, all of 1, just A is well defined. It doesn't call anything that might be reassigned. It doesn't refer to any globals. So we're good there too. And the arguments themselves are safe to evaluate. So we know the argument is 1, it's well defined. We can look at this and replace it with 2. Cool. The function itself is unused now, though, so we still have dead code. Dead code can be kind of annoying because it remains junk in your file. It might not be meaningful anymore, and in a lot of cases, obfuscations for a lot of malware I've seen will just insert many hundreds of lines of dead code just because. Dead code is pretty simple, though, in the low-hanging fruit sense. If nothing can reach it, it's dead code. If nothing references it, it's dead code. And if it's dead code, you can just remove that expression most of the time. So walk through the whole program and say, well, I understand JavaScript assignment rules. I know how JavaScript scoping works to know when things are getting shadowed, and I know how assignment works, so I know that in JavaScript you can pass the entire local scope as a variable to a function. If you get a dictionary in and assign to it, you might be assigning 2 local scopes of opposing functions. And after we consider all of that, if we're done and there's an expression that's never referenced, we can just remove it. Done. So in this particular case, literals, identifiers on their own, like if we just had some variable name on its own, or the string on its own here, that's always going to be dead code. There are a few tricks you can do to make removing that cause problems, but you can work around that as well. So we can go through and I'm going to show some Python that I've written where we walk through a program and say, well, is the code dead? If it's dead, can I remove it? So literally separate functions for each kind of thing in the program. We have assignments, expressions on their own are expression statements. So the important one here is if the expression is, if it's an expression statement and the expression is a literal, then we know it's dead code. Because it was an expression, it's a literal, there's no thing it could be doing, it's just a literal on its own. Same thing for identifier, a variable name. If it's a variable name on its own, all right, well, we can get rid of it. And then everything else is a lot of recursion on all of the things that could be in the program. So for a call, we ask the same question of the thing that's being called and all of the arguments, because we want to go through the entire program here, which is it's a decent bit of Python. So when we take this and run it at the obfuscated malware that I was showing before, even just removing dead code is useful because remember this was several hundred lines of multi-line spanning blobs of stuff, and it turns out that every other line in between these variable definitions was dead code, and we can just remove it. In addition, you could say, well, this expression is constant and add it all together. You can see how some of these might start adding up in interesting and useful ways. So, there is some weirdness to JavaScript, though. Did you know that empty array plus the number 1 is the number 1, but empty object plus the number 1 is the string 1? So empty array plus 1 is not exactly the same as empty object plus 1. And you can abuse this when you're trying to write something obfuscatory, when you're trying to just throw a reverse engineer, because maybe you use triple equals where that evaluates to false. 1 is not the same as the string 1. Or you use double equals where they're the same. And because double equals will try to turn things into, it'll try a little harder to say, do they look like they might be equal? Empty array plus 1 is the same thing as empty object plus 1, even though empty array is not the same as empty object. Similar kinds of things, 1 divided by empty array does not equal 1 divided by empty object, because no one might expect them to be equal, but I wouldn't expect them to be reasonable math expressions, but you will see them in some JavaScript. So on the left, it evaluates out to infinity, because the empty array evaluates to 0. So 1 divided by 0 is infinity. And the division by an object, because JavaScript rules, that is not a number. There you go. So these are no longer the same. So if you have if on an empty object, it'll take that branch and do the thing. But empty object is not the same as true. Like you'll see that it's false if you do empty object equals true. JavaScript object plus 0 is 0, but JavaScript object plus JavaScript object is a string. And it's a very nondescript string either. You just get object, 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 object. Except on Firefox, where that addition of objects comes out to nan. And you totally could do that for like platform detection if you wanted to know if you're being run in Firefox, or if you're in Chrome and you can abuse Chrome-specific features. There's some amount of work to be done in the future that is stuff that really isn't fitting for proof of concept of can we deobfuscate a little bit better, which is proper constant propagation. You'll see in compilers you'll have constant propagation. There's my particular favorite, the most powerful form of constant propagation is called sparse conditional constant propagation. The important thing about that is if you have something like a loop, you might not know if an expression in the loop is constant until you've gone through a few times. So you can start doing things where you say, well, is this value assigned conditionally going to be constant through loop? If it's going to be constant, then we've answered some of those questions before about is it safe to deal with, is it safe to change things here? In some of the cases where we've done some analysis and the function looks really simple, so it's x plus 1, maybe it makes more sense to replace the function call with just the text of the function. Replace a1 with just x plus 1. That can be tricky for all of the same reasons that any of the changes can be tricky, which is that some obfuscation tools will take your original code and they'll get the source code of it, because you can call toString on a JavaScript function and get that original string back out, compute like an XOR key out of it, and then use that to decode a string. So if you've gone through and changed the function at all, you now break that XOR key. So you'd want to do something where you ensure that if there's a reference to the original source code, you replace it with the original source code before you tampered with it, and then change the real function. And then one thing that would be nice here is more real-world test cases, because as much as I was digging, it looks like Google has gotten pretty decent at catching JavaScript spam. Things that were in my spam 6 months ago are gone now, and nothing more has come by. Looking around on the internet, there's like 4 major forms of obfuscation, but a lot of these things apply to languages that aren't JavaScript. They apply just the same to Python, to VBA, things like that. This worked. This is kind of the end. I think I went pretty fast, actually. So if anyone has any questions, I'm also going to be running this in the background. Anyone have questions about, shit, that didn't work. Try that again. Yeah, demo kind of worked. So if there aren't any questions about JavaScript deobfuscation, obfuscation kind of things, I am going to put these slides, which include all of the code that I've written for some of the deobfuscation that I showed. They'll be up. The slides are, obviously in a shell, but. I was going to say at the start of all this, I was surprised how empty the room was, and then the room filled up a little bit, and I was really worried that people like JavaScript and wanted to hear all about deobfuscating JavaScript.